Now there was quite a bit more material in Unit 3. We talked about atomic structure, development of the atom, the periodic table, and also nuclear chemistry. So if we start kind of looking at just our basic model of the atom, we started with Dalton's model. He had Dalton's atomic theory. He just said that atoms were just solid spheres with a positive charge. And then it kind of expanded from that. Thomson came next. He was the one that discovered the electron. His was the plum pudding or the chocolate chip cookie model. He thought electrons were throughout that particular atom. He didn't know where, but he knew there were positive and negative charges throughout. Then we had Bohr's model of the atom, which talked about the electrons. He knew there was a positive charge, but then he thought these electrons were in rings in different energy levels outside the nucleus, which this model is very similar to what we use today, which we know electrons are in orbitals. Also around the same time, we had the Rutherford model. Through his gold foil experiment, he was the one that discovered the nucleus, and then his electrons, that was the Jimmy Neutron model. He thought the electrons were just in various places outside the nucleus. So that's pretty much the development of the atom. So once we knew we had protons, neutrons, and electrons, we are able to count how many protons, neutrons, and electrons an element has. So remember, if you're given a symbol with a number up top and then a number on the bottom, this bottom number is the atomic number. That tells you how many protons, so this would be oxygen with 8 protons. This top number tells you the mass, and the mass minus the atomic number tells you how many neutrons. Also remember, if an atom is neutral, the number of protons and electrons would be the same, so this would be 8 electrons. Now if I had an isotope of oxygen, it might look something like this. We know that's an isotope because 17 minus 8 gives us 9 neutrons instead of our 8. So it's still referring to oxygen with 8 protons and neutrally having 8 electrons, but now it has 1 more neutron, so we call this an isotope. You probably remember the M&M lab with the isotopes, where we were looking at calculating average atomic mass. Remember, average atomic mass is the mass of all the isotopes that exist for that element. And also when you calculated the average atomic mass, you took the mass of your isotope times the percent abundance as a decimal, and then you continued to take the mass of the isotope times the percent abundance as a decimal, and then what you end up with is the average atomic mass. And that's where the values on the actual periodic table, those atomic mass, those decimal numbers, that's where they actually came from. Now the next part of the unit, we started talking about where those electrons were located. We know with the Bohr model that we said electrons were somewhere outside of the nucleus. And he believed, or once Bohr had discovered the idea of energy levels, they determined that within these energy levels there were s, p, d, and f orbitals, regions of space where we could actually place those electrons. So we can write electron configurations that represent different elements. Remember, if you write an electron configuration, this number, that's your energy level, so referring to the first energy level in the periodic table. This is referring to the orbital itself, so the s orbital. This tells you how many electrons are in that sublevel, so 1. So the element with the configuration 1s1 is hydrogen. So you need to be able to write electron configurations and pick out the element. So if I said to write the electron configuration for oxygen, up above we said it has 8 electrons, so we start at the 1s. So you would say 1s2, 2s2, 2p4. We don't need to completely fill this because we only want 8 total electrons. If you add up all of those exponents there, you will get the total number of electrons for that element. You can also use a shortcut if you would like for elements that have a little more complicated or a lot more electrons in them. So for example, if you had potassium Potassium has 19 electrons. So if you didn't want to write that all out, you could look the period before potassium and we could put argon in brackets, and that would represent 18 electrons. Then the only thing else you need to do is finish this out. Potassium's in period 4, so we start in the 4 in the S block, so 4s1. So there's 18 electrons plus the 1, give us the 19 for the potassium. Now really the last part of Unit 3, we talked a little about nuclear chemistry. And we said nuclear chemistry, these reactions aren't affected by changes in temperature and pressure and catalyst. They're just naturally going to happen. And we talked about 3 different types of nuclear reactions. We talked about alpha, we talked about beta, and then we talked about gamma. Also, you might remember if you have an alpha particle emitted that's decreasing the mass by 4, and it's decreasing the atomic number by 2. And you can see this as evident in the equation, and you know you have a nuclear reaction if you see one of these 3 particles. Beta particles don't change the mass, but they increase the atomic number by 1, because that neutron splits into a proton and an electron, so you have one more proton in that nucleus. And gamma rays are really just high forms of energy, so they have no actual effect on the mass number or the atomic number in an actual reaction. We also talked about the difference between fusion and fission. Fusion is the coming together of 2 nuclei to form something larger, and fission is the splitting apart. Then the last part was half-life, which you might remember flipping the coin to indicate the half-life activity. Remember, it's just the time it takes to cut something in half. So if you had 10 grams of a substance and you were told that it underwent 4 half-lives, how much would be remaining? Well, you could use the equation, the A naught times a half T over H, but it's easier if we just cut this in half 4 times. So if I cut it in half 1 time, I would have 5 grams remaining. If I cut it in half again, I would have 2.5 grams remaining. If I cut it in half again, I'd have 1.25 grams remaining. And if I cut it in half one more time, what would we have? 0.625 if I did my mental math correctly. That is how much of the sample would be left after 4 half-lives. So that's really the main points in Unit 3.